Hi, I'm Hannes,
Hello, I'm Dominic.
and today we'll talk about the sign and basis invariant networks for much better positional encodings on graphs to then use them in our GNNs. And if you want to join reading group sessions yourself, you find the links for that in the description.
Yeah, sure. Thanks, Hannes, for having us. So I'll speak first about the first half, and then at some point I'll hand over to Derek. And yeah, so we're going to talk today about sign and basis invariant neural network architectures, which allow you to process eigenvectors in a principled way. And this is joint work between Derek and myself, and also our collaborators, Lingxiao, Tess, Suvrit, Haggai, and Stefanie. So first, why eigenvectors? Well, eigenvectors occur all over machine learning, and their computation is at the core of many of the most commonly used algorithms in the field that are used on a daily basis. Examples include the computation of singular vectors and principal components, which are, of course, eigenvectors of certain data matrices. As well as that, there is matrix factorization tasks, which often use eigenvalue computation as a subroutine. And there is a number of important algorithms that can be recast as matrix factorization problems, including the famous node embedding algorithms, Notevec and its special case deep walk. And another example of eigenvectors that are commonly used are the graph adjacency matrix and graph Laplacian matrix. More on that now. So for an underlying graph, the graph Laplacian is defined by this matrix formula. This is the normalized graph Laplacian, where D is a matrix whose off-diagonal entries are all 0, and the ith diagonal entry is the degree of node I. A here is the adjacency matrix, which is a binary matrix whose ijth coordinate is 1. If there is a node between. If there's an edge between nodes I and j, and 0 otherwise. And throughout this talk, we're going to use lambda 1 through lambda n in increasing order, and v1 through vn to denote the eigenvalues and corresponding eigenvectors of this graph Laplacian. So the graph Laplacian's eigenvectors and eigenvalues are well known for capturing important structural information about a graph. The figure in the top right-hand corner here shows 3 important regimes. For small eigenvalues, the corresponding eigenvectors and the eigenvalues themselves capture important information about local community structure. Indeed, the 0 eigenvalue has multiplicity equal to the number of connected components of the underlying graph. In the intermediate range, these eigenvalues and their corresponding eigenvectors capture information about repeated motifs within the graph. For example, the eigenvalue equal to 1 has multiplicity, which can be incremented by 1 by introducing, for any given node in the graph, an additional ghost node, which has the exact same graph connectivity as the original one. And finally, large eigenvalues and their corresponding eigenvectors capture higher level structural information, with the very largest eigenvalues computing information about the bipartiteness of certain subgraphs. The figure shown in the bottom right-hand corner shows how these eigenvectors of the graph Laplacian can be used to color the nodes of a graph in a structure-aware way. In the top row, we have the colorings using eigenvectors from small eigenvalues. And as you can see, in this case, these eigenvectors are able to identify and give similar colorings to nodes that are in nearby communities. For larger eigenvalues, like lambda equal to 1 here, we see that this is capturing certain symmetries of the graph. This eigenvalue equal to 1 actually has multiplicity 2 in this case, and it's able to identify the symmetric component of the underlying molecule graph here. The eigenvectors of the graph Laplacian have been really widely used across all of graph machine learning before up until now. Indeed, you need look no further than the spectral graph convolution, which has been core to the development of many graph neural network algorithms. The spectral graph convolution gives a way to use the graph Laplacian to define learnable graph convolutions that are graph structure aware. Another important example of the application of the graph Laplacian's eigenvectors is to graph positional encoding. And this has been a really rapidly growing literature recently. The idea is simple enough, which is that we would like to add additional features to each node of our graph. And we would like these features to capture some structural information about the graph. One way to do this would be to take the eigenvectors of the graph Laplacian and simply concatenate them or a function of them thereof, which is typically known as the positional encoding. The hope here is that the prediction model, which could be any message passing graph neural network or a transformer or anything else, can leverage these extra node features to get improved performance. So now on to the main problem that we would like to consider in our talk today, which is how can we handle the invariances that are inherent in the structure of eigenvectors in a principled manner. More concretely, the problem we would like to address is the following. Oh, I think I see your hand is up, Hannes.
Yeah, so you're talking about this positional encoding, for example, like why do we even want that? I mean, we can also just do our message passing, right? Why do I want positional features?
Yeah, sure. So I mean, the hope here, right, is that you can add additional representational power. So people know that many graph neural network architectures are only as powerful as certain graph isomorphism tests. And by adding these additional node features, you may be able to increase the representational power. Similarly, if your prediction model is in fact a transformer, then there is no graph structure inherent in the prediction model itself, or it doesn't use the adjacency matrix information. And so in that case, you would need the positional encoding information to give some kind of information about that graph structure to the transformer.
Okay, so if we were to do, for example, the thing that you proposed or that you said there, that of taking all the eigenvectors and using them as a positional encoding, then what information do we capture that we, for example, don't capture? Or like, do we capture all topological information?
Well, that comes down to the expressive power of the graph Laplacian's eigenvectors. Which graphs can you distinguish using them? And I think, what is it? I think for graphs with bounded multiplicity of eigenvalue, you can use these eigenvectors to discriminate or to test isomorphism between any two such graphs. And there is generally really large classes of graphs that can have their isomorphism tested or distinguished using these eigenvectors. But it's not quite as powerful per se as testing the isomorphism of any graph, I believe.
Yeah, I think it's still kind of open whether you can do that in like a decent amount of time. But also beyond just like testing isomorphism, there's a lot of inductive biases that are very useful. Like Laplacian eigenvectors capture distances between nodes in the graph. We'll see more on that later. But so message passing neural networks, they don't quite do that.
Yeah, but
it's more like
I'm probably jumping a bit too far ahead, and you'll probably cover a lot of that in the talk. But yeah, just to recap, so now we, for example, take the Laplacian, calculate its eigenvectors and eigenvalues, and the Laplacian is just the degree matrix minus the adjacency matrix, or the normalized Laplacian, and then we calculate the eigenvalues, eigenvectors, and then we can use the eigenvectors as embeddings for our individual nodes, or like good. And that's the recap for everyone who maybe just joined, and then let's keep it going. Or Panli, you want to say something?
Yeah, so can I mention a little bit line about this, because I kind of investigated this for like 2 years. So I can make a few comments on the expressive power based on this. So basically, if we just compare like the point cloud, essentially is a lot of eigenvectors, we still suffer from the symmetric issue, right? So I guess what we are going to solve like in this talk. So basically, if we compare two graphs, we cannot like use eigenvector to compare them directly. So we can use the histogram of eigenvalues to compare, and that representation power is of course bounded. is actually bounded by something called co-spectral graph. So basically, if two graphs are co-spectral, then you cannot use this, let's say this positional encoding or histogram of like an eigenvector to distinguish them. So this is also like behind the distance encoding paper I have previously. So basically, because distance encoding and position encodings are kind of very relevant. But overall, the conclusion is, if we compare the spectrum of two graphs, no, we cannot achieve the universal approximation, or we cannot like distinguish any two graphs. So there are a bunch of graphs. As long as if two graphs are co-spectral, then we cannot use like their spectrum.
Okay, so co-spectral graphs are non-isomorphic graphs with the same spectrum, right?
Yeah. It's the same like histogram. Like eigenvalues.
Maybe we should go on a little bit with the presentation. And,
so, can I comment on that? Like, yes, we're going to talk about these eigenvector symmetries, like they have permutation symmetries and these basis symmetries that Professor Lee was talking about. So you can't compare them naively between graphs. Eigenvalues don't really have these symmetries; they're just numbers, so you can compare them naively. But if you do like some smart stuff, you can compare eigenvectors between graphs. Like we're going to show this later. It's like spectral invariance.
I understand. So the thing is, we can chat about that later. Chat about it later. Thank you.
I would like to jump in very quickly that in our paper on Sun, we actually proved that using the full set of eigenvalues and eigenvectors, we can distinguish any kind of graph and solve isomorphism. The number of parameters needed to solve this is probably non-linear, so it doesn't mean that a graph transformer solves this linearly. And what you are discussing right now is that with the eigenvalues, we cannot distinguish two graphs that are co-spectral. But with the full set of eigenvalues and eigenvectors, you can, in theory, rebuild the adjacency matrix, right? Because you can build the Laplacian matrix, and then you build the adjacency matrix, and you are able to really like understand the full graph. Anyways, I will let you continue the presentation.
Sure. So there's a lot of theoretical questions underlying the expressive power of these different Laplacian eigenvectors and so forth, different positional encodings. So I'll go on to consider the main problem that we'd like to address in this talk today, which is how to handle these eigenvectors, the processing of them in a principled way, such that we are addressing the inherent symmetries in them. So the exact problem that we set ourselves is the task of figuring out how to learn any arbitrary function on a set of eigenvectors and eigenvalues. In order to do this efficiently, we first ask the question of what invariances must a function defined on eigenvectors have due to these symmetries in eigenvectors. And then once we've answered that, we'll move on to the question of how to parameterize neural network architectures that have these required invariances built in so that they don't have to be learned by the model, and that are still universal in the sense they are able to approximate any function f defined on eigenvectors. So what symmetries do eigenvectors have? The first and most simple is sign invariance. So if you have an eigenvector v, then actually the entire subspace spanned by that eigenvector defines a set of eigenvectors with the same corresponding eigenvalue besides the zero vector. So if we're looking only at unit norm vectors, then whenever v is an eigenvector, then so is minus v. And when you run an eigensolver on your underlying matrix to compute these eigenvectors, it could return either plus or minus v. So there is a sign ambiguity there. There's a second, somewhat more complicated invariance that is also present in eigenvectors, which occurs in the case that there is eigenvalues with high multiplicity. When you have multiple different eigenvalues coinciding, there is multiple different linearly, or in fact orthogonal, eigenvectors corresponding to each of them. And so you have an underlying d-dimensional eigenspace. When you run an eigensolver on an underlying matrix of this form, it could return any valid basis of this eigenspace. And so since there are many different bases that could describe the same underlying d-dimensional eigenspace, we would want to also have a model that is invariant to the choice of bases that we use. And this effect of high multiplicities is actually frequent in real data and is not just of theoretical interest. And we have some statistics we computed on real data sets, particularly molecule data sets, showing that many of them have high multiplicities. This multiplicity effect is closely related to having repeated motifs within the graph.
Okay.
Yes, Hannes?
So we have a data set of a bunch of graphs, and now you're saying that it often happens that the Laplacian for it, or yeah, the Laplacian for it, if we calculate the eigenvalues, then we have often the same eigenvalue for many of the eigenvectors. Yeah, for many eigenvectors.
Correct.
Okay, and then why is that bad? Why is that a problem for us?
Because when you run an eigensolver to generate an eigendecomposition of this matrix, it will return in a somewhat arbitrary fashion or an opaque fashion any basis of that underlying eigenspace. Okay. And what's really important here is that underlying eigenspace structure. That's the real key thing here, is what eigenspaces correspond to this matrix. So we don't want any model that is defined to have a dependency or to be variant when you change the basis of that eigenspace.
Okay, so are you saying we usually order like our eigenvalues according to our eigenvectors in our positional encoding according to the eigenvalue, and that's the Derek, you're shaking your head?
No, it's more like you could. So this is just like a fundamental mathematical fact. When you have a high dimensional eigenspace, there's infinitely many eigenbases, and your solver can return any of those. So like, it's not like the order changes, it's like everything changes. Like even the order can change, or like you could rotate all the eigenvectors in one eigenspace. Yeah.
The core to all of this is that, well, an important thing that underlies all of this is that we're using vectors to describe, as points to describe vector spaces. So what's really important underlying all of this is the vector space structures of these different eigenspaces. But since it's difficult to define functions that operate on vector spaces, we use single points within those vector spaces, the eigenvectors, to describe those spaces. And so that is essentially the reason why we end up having all of these invariance issues or these symmetries, because we are actually using a single point in the space to represent that space.
Okay. Yeah. Perfect. Thanks.
Great. Yeah, so these invariances can be easily described mathematically. And you can write them in these forms for just a single eigenvector or eigenspace. So in the case of sign invariance for just one eigenvector, a function f defined on that eigenvector should have the same value whether you look at vi or minus vi. In the case of eigenspaces, we want our function to have the same value no matter which choice of eigenbasis we use. You can transform an eigenbasis, which can be represented as this column concatenation of all of the vectors in that eigenbasis. You can transform that eigenbasis into any other basis via right multiplication by an orthogonal matrix Q. An orthogonal matrix, recall, is a matrix such that Q times Q transpose is the identity. And so if we want to be invariant to the choice of any basis of this underlying eigenspace, what we want is for f of v to be equal to f of v right multiplied by any orthogonal matrix Q. This formulation can be easily extended to the case of multiple vectors or eigenspaces. In the case of multiple eigenvectors, we simply want the sign configuration of all n eigenvectors to be f to be invariant to that sign configuration. And in the case of many bases, so as before, we have vj's, which are stacking column-wise the eigenvectors corresponding to the jth distinct eigenvalue. We want to be able to apply any orthogonal matrix to transform each of those eigenbases into any other eigenbasis describing the same underlying eigenspace, and for our function f to remain unchanged in its value. There is sometimes one additional property we would like a model defined on vectors to have, which is permutation equivariance. This is important when f is actually modeling vectors coming from some underlying graph, since in a graph, there is no inherent node ordering, and yet we have to stack the features corresponding to these nodes into a vector and have to introduce an arbitrary node ordering. And so if we are defining an architecture on vectors coming from some underlying graph, we would like the output of that graph to be permuted according to some permutation G, if the input is also permuted by that permutation G. So sometimes we will want this additional condition. So now I'll move on to describing how we define neural network architectures that have these desired invariances. And I'm going to first talk about functions defined on just a single eigenspace or eigenvector. And then after that, I will hand over to Derek, who will show how to use these architectures defined on single spaces as core building blocks to build an architecture defined on multiple different spaces or eigenvectors. So first, sign invariance. Sign invariance can actually be quite easily characterized as shown in the following proposition, which shows that any continuous function which is mapping from a vector to another vector is sign invariant if and only if it can be written as this symmetric sum phi v plus phi minus v for some continuous v. The proof of this is actually really easy to see, since of course the necessity of being written in this form can be shown by any sign invariant f simply defining the corresponding phi to be f divided by 2. The converse, that if your f can be written in this form, then it is sign invariant, is immediately obvious. Furthermore, if you would like this f to have the additional permutation equivariance property that we mentioned, which will be important for graph learning problems, then this requires only that phi is also permutation equivariant. Using this decomposition, we are then able to parameterize arbitrary a universal architecture that is able to represent any continuous sign invariant function acting on a single vector. In the case of a general f, we can use any neural network architecture that can approximate a continuous phi, and so a continuous function. And so in particular, we could take phi to be multi-layer perceptron. If additionally we wanted f to have this permutation equivariance property, then likewise, we simply need to take phi to be any function or architecture that is able to approximate permutation continuous functions, such as a deep set or a set transformer. Did I see Panli is wanting to say something?
So sorry. So yeah, I personally, I don't want to interrupt, but yeah, since you asked, I just, so do we need a permutation equivariant here? So because I guess if we have this f function work on the, let's say, position encoding like the Laplacian eigenmap, already the components in that vector don't need, so we don't need, let's say, permutation equivariance anymore for that vector, right? So I mean, based on the entries of that vector.
I think we do, right? Because we want the output of this mapping, this sign invariant mapping, to then be concatenated to the corresponding node features, and the ordering shouldn't matter to that, right? The output of our sign invariant network.
Yeah, let me say this again. So if your v here is that a v-dimensional vector of the, let's say, n-dimensional, oh, perhaps I'm wrong. So your v here is more like each entry correspond to one node, right? Is that, let's say?
Yeah.
Exactly. Okay. I see. Then yes, it should be. Yeah. Okay, thank you.
Exactly. So there's two different dimensions here. I can scroll back just a second. We have, when we have this, we essentially have the along the coordinates of a given eigenvector, there is n different entries. And then there are n, or we could also truncate to have fewer eigenvectors themselves, so v1 through vn. And so here we're talking about permuting along the coordinates of each eigenvector. So yeah, there is two directions we could be permuting, and it is important which one we're talking about. So thanks for the clarification.
Yeah, thank you.
No worries. Okay, so that actually describes everything that you need in order to define these sign invariant functions in one space. And so now let's look at basis invariance on one subspace. So recall here, a function f is basis invariant if it's invariant under right multiplication by an orthogonal matrix Q. And so it actually turns out that any basis invariant function, which is mapping these matrices to a corresponding vector in Rn, can be parameterized in the following form of phi of V outer product with its self-transposed for some continuous phi. Now the invariance to the orthogonal matrix here comes immediately from the outer product structure here. Since of course, if you take the outer product of VQ with itself, then some simple matrix algebra shows that this is just the same thing as VV transpose. But it turns out that processing this outer product matrix is all that's necessary, i.e. processing with some phi is all that's necessary in order to parameterize this function f. If additionally we want f to have this permutation equivariance property again, then all that this requires is that phi is also permutation equivariant as a function from matrices to vectors. So in this case, when we talk about permutation equivariance of phi, what we mean is that if we permute the rows and columns of an input to phi using the same permutation g, then the output of phi should be permuted also according to g, but as a vector. Using this characterization, we are able to also parameterize universal class of functions that have this basis invariant property for a single basis, or for a single subspace. Again, all we need to do is define phi to be some architecture that is able to approximate any continuous function mapping matrices to vectors. And so for general f, we could take phi to be a multi-layer perceptron, which is applied to the flattened matrix. If additionally we wish to have this permutation equivariance property, then now we need to define a class of, we need phi to be a universal class of, a class that is able to universally approximate any permutation equivariant function mapping matrices to vectors. One instance of such an architecture is the invariant graph network architecture of Maron et al. The invariant graph network is a composition of many different permutation equivariant layers which map tensors to tensors. In terms of theory, in order for the invariant graph network to be able to approximate any permutation invariant function from matrices to vectors, the internal layers of the invariant graph network will need to process large order tensors, order n. And this has high complexity, like n to the power n. So that is what is required to get this theoretical universal approximation. But since it is in practice intractable, we will restrict to using only order 2 tensors, i.e. matrices. And so I'll hand over to Derek now, who will take it from here. And I think we're also going to swap over our slides.
Okay. Yeah. So see that? Okay. I'm going to talk about using the single eigenspace stuff to parameterize the functions we really want most of the time, which is like you have multiple eigenvectors or multiple eigenspaces. So yeah, just to recap, this is our goal. We want network F where we have this basis invariance. So you kind of have these eigenspaces V1 through VL, and you want to change basis in each eigenspace or hit it with an orthogonal matrix. In the case of sign invariance, like these are -1s and 1s, of course. But yeah, one way to say this is that you want F to be invariant to this direct product group on the right. These orthogonal, the orthogonal groups direct product with each other. And this is kind of what we're going to do here. We're going to abstract like to a little higher level. And we prove this decomposition theorem. And what it says is that, so basically we have a higher level result, which is for any direct product of groups, G1 cross GL. So under very mild topological conditions, every invariant F that is continuous, every F that is invariant to this direct product of groups can be represented in this equation as follows, where phi I is a GI invariant function. And what happens is that phi I processes like xi and it handles the GI invariance. So you process these guys independently. And then you have rho, which is kind of an unconstrained function that just aggregates over these independently processed
points. Also, the second result of our theorem is really important. It says that if GI equals GJ, or that is like two of these symmetries are the same, then you could take phi I to be equal to phi j. So whenever you have the same symmetry, you could process it in the same way, okay? And what does this mean for us? So the takeaway is, as long as you know how to make phi I, or as long as you know how to do GI invariance, you can get the direct product invariance, G1 cross GL. And this is really important because it's a lot easier to do GI invariance. It's a smaller group, right? So for the sign group, the direct product group is of size 2 to the L. You have to handle 2 to the L different sign configurations. But the sign group for one dimension is just of size 2, right? It's just -1 or 1. So that's just like a lot easier. You only have to handle 2 cases, right? And also these GIs, that's like the single subspace case, which Josh covered. So we're going to directly use that in our next slide. So I just put the theorem on top again, but you can look at the bottom. This is what we call our sign net architecture, which is our sign invariant neural network. So for eigenvectors V1 through VL, what happens is you independently process each eigenspace with this phi of VI plus phi of negative VI, you see? And this handles the sign invariance on one eigenspace, the 2 sign flips. And then you aggregate across all of these independently processed eigenspaces with rho, okay? Hannes?
Yeah, and then you use that as additional feature for each node?
Yes, yeah. We're going to show one more picture of the pipeline later, just to be clear. But yeah, you concatenate this F of V1 through VL to your node features in most pipelines.
Okay, and why don't, and what happens if I just take the absolute value of V1 up to VL?
So there's a lot of reasons I could tell you why this is bad theoretically. Like it's not injective. It breaks like the distance properties of Laplacian eigenvectors. Also, for those people who don't care about that, we show in experiments that it's not that good most of the time. Yeah.
Nice.
Yeah. So you'll see that soon. But yeah, so our theorem actually is very general and it actually covers this case. If we do not care about permutation equivariance, sign net is universal. Okay, if we're using the non-permutation equivariant version. Of course, permutation equivariant universality is sometimes difficult, and we don't know whether sign net is universal if we're making these permutation equivariant. But yeah, if we want sign net to be permutation equivariant, we make phi and rho to be permutation equivariant. And here we give choices you can make. You can make rho and phi be MLPs that act on each node independently, or deep sets, or transformers, or GNNs. Also, you could add eigenvalues as arguments, or like node features if you want. And what you do is you could just add it into phi, or like add it like to rho basically, and you don't have to like negate the eigenvalues or anything else you want to add. You could just add them right in. Yeah, and we often use phi as a GNN sometimes. You'll see more of that in our experiments. But yeah, just to make it like really clear, once again, rho processes each eigenspace. And one more point I want to make is rho, you see there's only phi, you see there's only one phi, right? That's because of result 2 of our theorem, which says that you could share the phi i's if the symmetries are the same. So this makes things a lot more efficient than parameterizing separate phi i's. But yeah, once again, phi processes each eigenspace and handles the sign invariance on one eigenspace, and rho aggregates across all eigenspaces. So when you negate a vector, you just kind of flip it across the origin. So that's kind of what this picture is showing. Yeah, and that's how sign net works. And now for basis invariance, we apply the same theorem, which is very nice. And what we do is we have these phi of di now. So, and these phi of di, they are invariant graph networks that operate on these matrices, vi, vit. where VI-VIT, if you're curious, is actually the orthogonal projector onto the ith eigenspace, which is pretty interesting. But yeah, like Josh was saying, this is kind of the, like one phi of DI is the architecture you want on one high dimensional eigenspace. And we're just doing it independently to all high dimensional eigenspaces and then aggregating with rho. So these phi of D are these invariant graph networks, once again, that take the matrices and they output like vectors. And we're going to keep them at order 2, which means they only make matrices. They don't make higher order tensors. So for the rest of this talk, we'll keep them at order 2. But I just want to say in our paper, we have this thing called expressive basis net, where we make IGNs like really big, like humongous tensors. And this is like a nice theoretical construct for like universality results, but we're not going to talk about it much here. Question?
Do the phi all have the same parameters?
No. So you see how I put phi of DI?
Yeah.
You have a separate phi for every dimensional eigenspace. Like you have one phi that handles one-dimensional eigenspaces, one phi that handles two-dimensional eigenspaces, and so on.
Good.
This is from result 2 of our theorem, because the GI is equal to GJ only if the dimensions of the eigenspaces are the same, right?
Good.
Make sense?
Makes sense.
Yeah, so I almost forgot to mention that. That's very important on this, yeah. You only need one per dimension of the eigenspace you want to handle.
So I have a question here. So for, let's say, 2 eigenspace, so when you mention GI equals to JJ, you mean these two have the same dimension?
Yes.
Or, yeah, so in that case, do we need to let the corresponding phi equal to each other? So, or we can use, I guess we can use different phis, right, for different cases.
Yes.
So it's still fine, right? Yeah.
Yeah, precisely. It's still fine. Yeah, so you might want to like try like using a separate phi for like the low frequency eigenvalues and like the high frequency eigenvalues of another phi, for instance. We don't really do that in experiments. We tried it at some point, but it didn't work out in preliminary experiments. So we just stuck with sharing as much as possible. Yeah.
I see. I can imagine maybe empirically we just want it share, but theoretically it's fine. It will not break like equivariance in something, right?
Exactly. Yeah, it won't break.
Yeah, and another question maybe more on the higher order, let's say universality part. So I guess the assumption behind that is more like that phi d, let's say that phi function which works on that matrix could be universal. Is that correct? Yeah, so it's work on a matrix and it could be universal or in some sense. Yeah.
Yes, universal in terms of
permutation
equivariant, yes.
Yeah.
Yeah, exactly.
Yeah. So basically, kind of we assume that we have a very, very strong, like let's say isomorphism tester to build this phi so that overall we can be universal, right?
Yes, exactly.
Yeah. Okay. Great. Thank you.
Yes, that's exactly what it is. And one interesting future direction is like, do we need actually that strong of a phi? Because these are really structured matrices, you know, they're orthogonal projectors. Also, like if you have like a one-dimensional eigenspace, these are like rank 1 matrices. If you have a 2-dimensional, these are rank 2 matrices. So maybe you don't need higher order, but higher order is sufficient. Higher order tensors are sufficient for sure.
Okay, great, thank you.
Yeah, I hope someone looks into that. But also we have, okay. Actually, I think I'm about finished with this slide. And rho is just an MLP deep set sort of transformer. It just handles like node features, again, this rho, right? Cool. Okay, then we're gonna go into both theory and experiments at the same time, especially for graph machine learning. So this is the kind of diagram I was referring to earlier. Just to make things really clear, this is how we use SignNet. We take the graph adjacency and the node features. We just wait a minute. And then we have eigenvectors. And then we process the eigenvectors with SignNet. And then we concatenate the processed eigenvectors back to the node features all the way on the right to use in a prediction model like a GNN or a transformer. You could also, once again, you could also put eigenvalues or even put the node features inside SignNet too. But this is how we do it mostly.
Okay, so just sorry again. We take our Laplacian, we calculate the eigenvectors. Now we have our like an eigenvector here and another one here and so on. We take k of those.
Yeah.
Then you just put the first one here into this phi, and then you put the first one but negated into the phi, but we always have the same phi here, right?
Yes. Yes.
All the phi is, we always have the same weights here. And then we take the output of this row and concatenate it to our node features. And that's then the input to our GNN or whatever we want.
Precisely, yeah.
Thank you. Tom?
And Dominique?
Yes, a few questions on there. So rho is an aggregation function, like basically sum or mean or max or something like that. What is the rho exactly?
Okay, so if you're using a fixed number k of eigenvectors on each graph, then you could take rho to be an MLP even. You just kind of, yeah, you could take it to MLP, you see?
Okay.
Dimension by the embedding dimension of phi.
Yeah, but
okay, yeah, that makes sense.
When we do all eigenvectors of a graph, we'll basically take rho to have like a sum across all eigenvectors and then like another MLP. It's kind of like a deep sets.
Yeah, it could be a deep set. Okay.
Yes.
Another question here, like you use all these eigenvectors and you concatenate them, and then you pass it into deep set or into any kind of other aggregation function. But do you also provide the eigenvalues? Because by using only the eigenvectors, like there's an ambiguity on what frequency is V1, like because you could technically take this one here and this other one here and permute them, right? There's no way for the network to know which one is the low frequency, which one is the high frequency, unless you use some kind, also add the lambda 1 here, for example, or during the deep set part.
Yeah, exactly. So we actually, for the most part, find that we don't need to add the eigenvalues in for our experiments. And it's so one interesting thing is if you have a fixed number k of eigenvectors, then your rho, if you choose it to be an MLP, it knows like which one is like the order, like this is the first eigenvector, this is the second, and so on, right? But if you take rho to be like a deep sets and it just sums over eigenvectors, it has like no idea about like the order of eigenvectors. And the interesting thing is that this works really well on zinc. For some reason, it doesn't need to know the frequency. It doesn't even need to know the order of eigenvectors on zinc. And it just like does really well.
This really surprised us.
Yeah, I think one of the reasons could be, for example, that zinc is an artificial data set that focuses on local structures. So perhaps to get good results on zinc, you just have to get really good unique identifiers for each node. But I would assume, for example, if we're working on with a transformer, that then the frequency is very important because it tells you like what's the actual distance between the two extremities of your like between the high values and low values within your eigenvector.
Yes. Yeah, exactly.
Yeah. And I agree though that the MLP gives you an idea of distance. Like if you're working on data set with only one graph, for example, with Cora, well, in that case, you don't need the eigenvalues because the network can implicitly learn the eigenvalues. When you're working on data set of molecules where each one has different eigenvalues, then it becomes more important. But as you said, the MLP kind of captures at least the ordering of the eigenvalues and not necessarily which eigenvalue you're looking at.
Yes. Yeah. I agree. It's like it's almost sad that it works so well on zinc. But yeah, it'd be nice to see more people try different things with the eigenvalues. One easy way to deal with the eigenvalues is like concatenate them to phi. Another one I wanted to try, but I haven't, is like, there's this thing called like the GPS embedding, I think, in like graphics. You just like, you scale each eigenvector by like the inverse square root of the eigenvalue. I hope someone, yeah, maybe we'll try that actually. But yeah, it would be nice to get the eigenvalue information in there.
Yeah, I'm also in another project I'm working. I also want to try this scaling. Well, not by the squared inverse, but just by the inverse of the eigenvalue. So that way, the distance is directly encoded within the eigenvector. Because if you normalize the eigenvector, you lose the actual notion of distance. You just capture with what is far, what is close, but you lose the actual distance. But dividing it by the eigenvalue, you still capture that distance.
What's the intuition why dividing by the eigenvalue is better than just multiply or just concatenating it?
Because the after you divide by the eigenvalue or divide by the square root, I've seen you when you take the inner product of the eigenvectors, it's like more meaningful, and like when you interpret this as a manifold. Okay.
Okay.
When you're dealing with like, okay, I'll just send a paper. You know, I'm not even gonna ramble. Okay. Emmanuel had a question.
Yes, so a couple of very quick comments. I don't want to waste time. So the GPS inner product is the green function on the manifold. So that's why it is so meaningful. So the second point is that, so actually the network has access to the Laplacian, has access to the eigenvectors, so it can compute the eigenvalues directly. So maybe it's not so surprising that you don't need to input the eigenvalues explicitly.
Oh, wait, can you explain it to me again?
So if the network has access to the Laplacian and to the eigenvector, you can compute eigenvector transpose times Laplacian times eigenvector, and you get the eigenvalue.
Why are we saying that we have access to the Laplacian?
Don't we? So isn't phi or rho using the Laplacian operator?
Actually, this is a good point. When phi or rho is an MLP or something like that, no. But actually, in our zinc experiment, we take phi to be a graph neural network, like a graph isomorphism network. I'll show that actually.
I see.
So yeah, you could in theory hit the eigenvectors with the Laplacian or the adjacency or whatever.
But then don't we have the same problems like the way that we can't capture some patterns in graphs like other GNNs can't?
But it's like, yeah, kinda. But you're not like, it's a little different because your node features are like eigenvectors. But yeah, in theory, I do agree. In theory, it's not clear how strong this is. But in practice, which is what this slide is on, we found that using a graph isomorphism network for phi in zinc, at least, it like works really well. It just like boosts performance a lot.
Then I could, okay, in practice, but I just don't understand this Laplacian argument, like why we don't need the eigenvalues. Yeah, why we don't need the eigenvalues, because then otherwise I could also just say, right, if I concatenate to the eigenvectors to my node features already, or not the eigenvectors, like your positional encoding to my node features, and then in the node features you have, or after you've created your new node features, now you do message passing with the adjacency matrix as well, and then you have the Laplacian available.
Yeah, that's true. It just, I think we're getting a little too into the weeds of what this may or may not be doing. But yeah, it's like, you know, ideally we would have just eigenvalues at the start or something. I don't know if, like Emmanuel said, we're really implicitly computing the eigenvalues inside net. I kind of doubt it actually, but you could in theory.
Yeah, so Emanuele, would you say it's like, am I missing now something obvious? And the Laplacian is available in some obvious way, or do you just mean it is available in the sense of us using a GNN?
Yeah, so I was figuring that either phi or rho were using a GNN. So in that sense, I meant that the model has access to the Laplacian. But Derek, he says something interesting, that with an MLP, it still seems to work well. That's admittedly very surprising to me.
I don't think it works that well on zinc with an MLP. I don't remember the numbers, but yeah. Okay.
All right.
I'm gonna move. Yeah. Okay. So sorry, I have this like big table. But what's in this table is like our performance on zinc, 500K parameters. It's like a molecular graph regression task. So what we have is SignNet performance.
Well, actually, then I think it's pretty relevant. Dom, do you want to repeat again what zinc is in terms of a molecular regression task?
Yeah, so zinc is just like a task for predicting a combination of the computed lipophilicity score and the computed synthetic accessibility score. It doesn't mean anything for someone in machine learning, but basically these two tasks are actually linear estimation developed by chemists about the real physical quantities. And these approximations depend only on local structures rather than global structure. Like it basically like count the number of rings with nitrogen, count the number of nitrogen oxygen double bonds, and these kind of things that happen within the zinc. And then it sums them all with a different weight. So with zinc, as long as you're able to understand local structure very well, you can really improve on the results. Whether the global structure or adding transformers or things like that is not expected to work that well on that data.
How do we get the ground truth information for zinc?
With the RDKit package, like you just compute them, it takes like 1 microsecond per molecule.
Okay, so it is something that you can, that just depends on the structure of the molecule.
Exactly. You could, in theory, take all known molecules in the universe and compute the zinc, the property here quite easily.
Okay, good. And now, Derek, we have some really nice results.
Yeah, and we are good at doing whatever Dominique just said. So in our table, we have SignNet, and we also have all these eigenvector baselines, and we beat all of them. What I mean by this is like, you could feed in the eigenvectors and like flip the signs randomly, as a lot of people have done in the past with data augmentation, or you can take the absolute value of the eigenvectors, as Hannes is circling almost, and as Hannes asked about earlier, that kind of sucks. But yeah, basically we beat all these eigenvector baselines. And we compare, if you compare, it's not in this table, but if you compare against other positional encodings, we beat them. On zinc, 500K for whatever task this is, as Dominique said. And our PNA result, when we use PNA as the prediction model, principal neighborhood aggregation, and when we have SignNet as the positional encoding, we essentially get state of the art, except for this thing called SIN. So I think except for this thing called SIN only. They do pretty well. They have maybe some people would call it domain specific information, like what structures in a molecule are important, the rings and stuff. But eigenvectors are kind of domain agnostic, which is nice. Anyway, we do really well, basically. Yes, thank you. My cursor is like not appearing, so I can't draw these myself. Thank you, Hannes. And then, yeah, basically, as I said, we have phi to be a GIN, which is really important, and rho to be an MLP. Cool. Let's move on to like theory.
Yeah, sorry, something very quick about the previous results, and something that really surprised me, and I think we should highlight it, is that in the history of positional encoding, no one has ever seen that using the full Laplacian values and eigenvectors was better than using just the first 8 or even the first 2. And in your work, it's the first time that I actually see this. Like, using more than 8 eigenvectors is helpful. In most cases, it's actually adding more noise. So I just want to say congrats on that.
That is a good point. I really can't believe I forgot to mention that. Yes, we use all eigenvectors. Maybe one theoretical reason you might expect our method to work better with all eigenvectors is that like the invariances, they exponentially increase. Like the sign group exponentially increases as you increase the number of eigenvectors. So maybe we can handle that better. That's just a complete theoretical guess as to why. But yeah, I think it's much nicer to use all the eigenvectors. You have a lot more information. Okay. Now there was, as Josh said, there's so many positional encodings in the literature, and one may ask like, oh, what's like, which one should we use? Well, at least in theory, our method kind of subsumes a lot of positional encodings. This is in theory, but what I mean is that our sign net with the Laplacian eigenvectors and eigenvalues, it could universally approximate all these other positional encodings on the screen, sign net and basis net. So in theory, if your network really wanted heat kernel positional encodings, sign net and basis net can compute that. Or maybe it wants random walk positional encodings, and you can compute that instead. So it's kind of moving towards like a very nice universal spectral positional encoding, if I may say so myself. Okay. One other universal spectral thing is these spectral graph convolutions that Josh was talking about. This is a very important class of functions. It's these functions H in the middle. So you kind of have like a polynomial of your eigenvalues and you like hit it on your node feature matrix. This captures important things like heat kernels on graphs and generalized page ranks. And also they're like the basis of spectral GNNs. But what we see is that sign net and basis net can compute these, can universally approximate any single spectral graph convolution. And actually it does so in a very simple way. Like you see a sign net, you just got to make the phi equal to that thing and the rho equal to a sum. And it's like a very nice simple functions intuitively. You could like formalize the simplicity of these functions by the framework of algorithmic alignment by Kielu and his co-authors and Stefanie in our lab. And basically what this algorithmic alignment says, like when you are learning like low degree polynomials, your neural networks tend to do better at that in terms of sample efficiency. And yeah, these are kind of low degree polynomials of the input as you see, as long as P is kind of simple, right? And then basically in synthetic experiments where we want to do regression on where the regression output is a spectral graph convolution, the regression target, we do pretty well. So basically we're going to make rho and phi to be like deep sets transformer IGN. So you don't have any message passing in there. And what we see is that even without the graph structure in our sign net, we could beat all the eigenvector baselines, and we beat message passing neural networks. And we actually often also beat spectral GNNs. Yeah, we beat the eigenvector baselines by quite a bit. I don't even like plot them on this chart. And we beat many of the spectral GNNs. I've kind of pulled them into like one y-axis here, if you even look at the chart, but there's like a few spectral GNNs we tried against. So that is very nice. And it's kind of known that message passing neural networks are a bit constrained in like the spectral stuff they could learn. So it's nice that we could universally approximate all spectral graph convolutions.
Can you summarize that how they're constrained? Do they always just learn low frequency or high frequency signals, or capture low frequency or high frequency signals?
Yeah, in theory, these message passing neural networks, they are usually low pass filters, meaning they only capture low frequency information.
Okay.
In theory, this doesn't always hold, but there's a lot of papers that say stuff like this.
Yeah.
So I personally don't think so. So GraphSage can capture high frequency, right? So the only way is you just need to take care of one node itself and its neighbors in a different way, then you can handle high frequency. But if we do graph convolution, yes, it's only low frequency. That's correct. Basically, if I use graph stage, I use my own feature to minus the aggregation of the neighbor feature, then essentially it's a high frequency.
Exactly. Graph isomorphism network is similar too. You could do something like that. Yeah, but it's like certain GNNs are biased towards that. Not all.
Yeah, my feeling the difference between here, like the traditional message passing GNN is bounded. We know it's bounded by 1WL, so it's always bounded by 1WL. So no matter what kind of like let's say layers you use. So, but the spectral GNN is one way beyond that. So it of course can break 1WL, but of course spectral GNN also have its representation power limitation. It cannot like distinguish something called distance regular graph or strongly regular graph. It cannot distinguish. Yeah.
Yes. It's very good insights.
Okay, then because we got so deep into this topic now, I want to find out that we previously had Muhammad Al-Shila presenting his paper analyzing the expressive power of graph neural networks in a spectral perspective. If you care about that, it's in the chat.
Yeah, that has some of the insights about GCN and GAT, also GIN. But yeah, this is why I was so careful about how I was saying GNNs are a little limited in their spectral power. It's kind of nuanced, actually. But yeah, you should check that out. But one thing that is not nuanced is that GNNs cannot compute the stuff on this slide, but our networks can. So this is what I'm going to talk about. These are, okay, when we like study the expressiveness of GNNs, like you see the same things in like a lot of papers, right? It's like, okay, guys, GNNs are like bounded in power by Weisfeller-Lehmann. So we're going to use like these combinatorial invariants and algorithms to study GNNs. But actually, there was like a lot of other work on graph isomorphism testing, and like maybe fields like complexity theory or spectral graph theory. I don't know what they really called it back then, but there's these things called spectral graph invariants, which capture a lot of information about a graph and like try to test isomorphism too, using just spectral information. And there's these things called graph angles, which are probably the most popular spectral invariants, besides like just like the set of eigenvalues. And graph angles are this in this formula right here. It's the projection onto the ith eigenspace of the jth standard basis vector. So there's like a solid amount of them. And these are permutation invariant, basis invariant, and so on. I mean, they're permutation invariant if you stack them in a matrix the right way.
So we have n squared of these angles.
If you have higher multiplicity, if you have like k eigenspaces, you have k times n. But yeah, if you have distinct eigenvalues, it's n squared. Yeah.
Okay.
Yeah. So actually, basis net, we can universally approximate these guys, these graph angles. And what this means is that people studied graph angles in the past, so we're just gonna copy and paste their results. And then we know that basis net can learn to count the number of 3, 4, or 5 cycles of a graph. It could learn to tell whether the graph is connected or not. And it could learn the number of length k closed walks on the graph. And actually all of these message passing graph neural networks cannot learn. So just by learning the spectral graph invariant, we do very well in terms of the combinatorial stuff we could learn as well. And actually, I want to talk a little more about these guys. I think these are a really promising avenue to study expressiveness of GNNs. I don't think they're studied that much in the GNN community right now. We're kind of stuck on combinatorial invariants. I mean, there's a lot of good reason for studying combinatorial invariants, like Weisfeller-Lehmann. I mean, message passing, aligns very well with that. But I think this is a very interesting theoretical avenue and possibly could lead to a lot of interesting work in GNNs. But yeah, and we just did experiments on counting substructures. So counting subgraphs in synthetic graphs. And what we find is that Laplacian eigenvectors actually help quite a bit. This is with sign flipping data augmentation, but SignNet boosts the performance a lot on top of that. So SignNet does really well for counting substructures, as maybe the fact that we can compute spectral graph invariance suggests. Okay, visualizations. These are molecule. This is a molecule I got from Wikipedia, selected at random. And the eigenvectors are plotted on like the top row, the normalized Laplacian eigenvectors. They're plotted as like kind of like node features on the graph, you see? So the white is kind of like close to 0, and the purple and orange are like high magnitude entries. And you see like on the top left, the low frequency eigenvectors, they capture like stuff that varies smoothly over the graph, and the high frequency eigenvectors change between neighbors a lot. And what we find is that when we take the output of SignNet, so the entire SignNet trained on zinc, rho and phi and everything, and we put all eigenvectors through that, we're going to take the first few principal components to see what SignNet thinks is important. And what we find is that like SignNet learns really interesting structural information. If you look at this bottom row, like for instance, SignNet, the first two principal components, they capture like these dangling oxygens on the side, and like this third one is really interesting to me because it like highlights the really congested nodes, as you see there, like those carbons and stuff. And if you look at all the
I don't. Like as you see there with those carbons.
Oh, the third principal component. So it's like the third column, bottom row. You see?
Yeah, and then what do you want us to look at?
It just looks. It's just like it's like the high traffic nodes. I forgot what this is called.
It's the min cup.
Yeah, stuff like that.
It's identified the cup there in the middle.
Yeah, but also it identifies those like carbons that kind of like connected to those dangling oxygens.
Okay.
If you just treat molecules as a graph, this looks pretty cool. And the Laplacian eigenvectors, we've plotted all of them in our paper, but like none of them, like they don't really match up with these SignNet principal components. So the SignNet captures some other structural information, which is possibly pretty interesting. And yeah, once again, SignNet uses phi as a gin, so it does message passing. Okay. And one more thing is we're going to do some stuff with Laplacians on surfaces. So this is kind of, so these discrete approximations to the Laplace-Beltrami operator on manifolds. It's used a lot in a bunch of fields like graphics, geometry processing. And what they do is they have an approximation to the Laplace-Beltrami operator with these discrete Laplacians on triangle meshes, like the cotangent Laplacian. It's basically just like the graph Laplacian on the triangle mesh, except it's like you have certain edge weights that are computed based on those angles in the top right. So I've plotted one of the eigenvectors of this cat triangle mesh on the left, like it's like purple and yellow. It captures a lot of structural information about triangle meshes. And we're going to do a texture reconstruction task. Yeah.
Yeah, I had a question. I've been actually working on a discrete Laplace-Beltrami operator research. Is this something that you formulated, or is this sort of a known? Because yeah, I was curious exactly whether you derived that directly by discretizing the continuous Laplace-Beltrami on a manifold, or what, how you came up with that. And then how you deal, like, do you end up with a symmetric matrix? Do you have a full set of eigenvectors for that operator, the Laplace-Beltrami?
Yeah, so I did not come up with this. Someone came up with this when I was very young, or probably when I wasn't born. In graphics, I think. Actually, I don't know which community first came up with this, but it's used a lot in graphics. I could send you a link. But what happens is these edge weights, it makes it so that it's not a symmetric matrix, the Laplacian. But what happens is these edge weights are defined per like row. So you take that diagonal matrix defining the edge weights and you put it on the other side of the equation and you make it a generalized eigenproblem. And then this generalized eigenproblem has the orthogonal eigenbasis.
Okay, interesting. Yeah, if you could send a link on this on the channel, that'd be awesome. Thank you.
Yeah, I'll send it on the Slack. Yeah, yeah, and this generalized I don't want to talk about the generalized eigenvector problem because it has like the same symmetries, or it definitely has sign invariance, and that's what we're going to do. So we're going to do this texture reconstruction task on a triangle mesh. So basically, given a point on the surface and given the values of the eigenvectors at that point, we're going to output like the RGB value of the surface, like what color the cat is at that point on the surface. And basically what people have done is this is very recent.
How's that well defined? Like your input is just a point on the surface.
Yeah, so this is yeah, that's exactly it. It's like an implicit neural representation. So your input is a point on the surface and the values of the eigenvectors at that point. So these are eigenfunctions. So the eigenfunctions take a point on the surface and they give you a scalar value.
Okay, and like, I mean, how do you know that all cats have the same color at a certain point?
Oh yeah, no, for this implicit neural representation, you are learning it for one cat.
Okay, good.
Yes, sorry. Your training points are like samples on the cat surface, and you want to fill in the rest of the fur and eyes.
Good.
Snout.
Makes sense.
Nose. Anyway, what people did was very recently they parameterized this RGB value with the Laplacian eigenvectors as just an MLP, like a lot of implicit neural representations do. But what we propose to do is we just put a sign net before that because the eigenvectors have the sign ambiguity, right? And I haven't put the numbers up, but we improve on this as well. I mean, we only test on like one cat model, kind of like they do. They also test on some other model. But it's like a proof of concept. I think our thing could be very useful for people in working with this kind of data. I think our SciNet could be very useful for that. Because I have heard from someone that, sometimes people will use like absolute values, say, or maybe sometimes people propose to use absolute values, but they can also use other things like use like the spectral graph convolutions that we mentioned before, and those have all the right invariances, but you have to be careful when you use these eigenvectors. And if we visualize the output of SciNet trained on texture reconstruction, we see some pretty interesting things. So you see, like I've plotted the eigenvectors, like 4 eigenvectors, and then like to the right, I've plotted the output of phi from SciNet, or like the first principal component of the output of phi. And one interesting thing we see is that SciNet learns these bilateral symmetries. So if you like slice the cat in half, like between the ears, like down the tail, the SciNet output is like symmetric across both sides, whereas not all the eigenvectors are, like eigenvector 14 is not on the top right.
And indeed, the cat's coloring is symmetric, right? The underlying pixels are symmetric.
Yeah, and yeah, exactly. The texture we want to learn is symmetric, but this has this bilateral symmetry. So SciNet kind of learns that symmetry is useful, which is nice.
Derek, sorry for interrupting, but if you have a global symmetry like in this cat, then all the Laplacian eigenvectors are symmetric or anti-symmetric. So actually, eigenvector 14 also has the symmetry information.
Yeah, so you mean like if you like negate it, right?
Exactly, yes.
Yeah, so Okay, that's what I suspected as well. Okay, but basically, if you use SignNet, or if you take the absolute value, is that
Exactly.
right? Yeah, if you
Yes.
take the absolute value, you will do this.
Yes.
I
You would
guess-
see actually a nice path going along the plane, the symmetry plane.
Yeah, so
you
I guess
take
what
that
we
one.
mean is that no matter
Mhm.
what SignNet learned, it's going to be bilaterally symmetric.
Mhm.
Okay, so anyway, no matter what SignNet learns, it's going to be bilaterally symmetric, but it learns useful bilaterally symmetric stuff because you see, like, it captures those ears intuitively. I could, you know, you never know with neural networks, but intuitively, this is kind of cool. Okay, that's all we have.
Just a suggestion. Maybe you want to take the cat, look at some deformation of the cat, like isometric or near isometric deformation of the cat. And then maybe you will observe that your phis, I mean, your basis functions, they preserve the symmetry better than the eigenvector. So the eigenvectors are very sensitive to deformations, and maybe yours are not so sensitive. So that would be very useful.
I see.
You see what I mean?
Do you mean, yeah, okay. So do you do a deformation and then compute the eigenvectors, or do you compute the eigenvectors due to, no?
So you take the cat, and then take a deformation of the cat, for example, jumping cat.
Mhm.
Okay, and then you compute the eigenvectors.
Okay, yeah, I see.
You will see that they try to be symmetric, but you lose some symmetry. And maybe with your area, you don't lose.
I see. Yeah, yeah. So I've been thinking about something related to this, which is, I think when you have these invariances, you could generalize better across different, like, graphs or triangle meshes. That might be a very interesting way to test that. Thank you. Yeah. Okay, but we're done. Oh yeah, so this is just like the summary slide. You could take a look at all the stuff. But yeah, any other questions?
Okay,
Johannes
first. Hey. Thanks a lot. Fantastic talk. Very nice work. I have one question. Did you analyze the output of your phi function? What I'm asking is, you input the projector of the eigenspace, right? And then I suppose you map this to an alternative basis for this eigenspace, isn't it?
You mean with our network?
Yeah, like the output of your phi function, will this be an optimal basis for this eigenspace, or how could the output of your invariant mapping be interpreted?
Yeah, I wouldn't say it's like an alternative basis. It just learns something. I don't really know how to interpret it. Another problem is, like, phi you could output like any dimension you want for phi. You know, like phi can output like 100-dimensional vector if it wants. So yeah, I don't know how to interpret it like that.
But again, what might capture something useful.
Yeah.
Or interpretable.
Sorry, I didn't hear that.
But perhaps the principal components might capture something interpretable, but we didn't look at that.
What inspired my question is that there's a really good researcher, he's called Carl Rowe, and he's looking at rotational invariance of eigenvectors. And he finds that rotational invariance is resolved by using the sparsest possible eigenvectors. Somehow this is an old theorem, or like not theorem, but an old theory, that rotating principal components in principal component analysis such that you get the sparsest possible principal component give you the best performing or most interpretable principal component. And I was wondering whether with your basis net you could confirm somehow this theory, that it would be really cool if your basis net
took a high dimensional space and always outputted the sparsest possible basis for it, this would somehow lead to an agreement of different literature branches.
I see. I see. You mean like the Varimax stuff?
Yes, exactly. It's the Varimax transform that he works on. But probably you understand it better than me. What is your take?
No, probably you understand better than me. I didn't really read it. I just saw the pictures. So yeah, I don't know. I don't think that BasisNet would learn this intuitively, exactly, of course. Yeah, that could be very interesting though to look into. And as for taking like those sparsest principal components as input to a neural network, I wonder how well that would work, because that would have the invariance, right? Yeah, I'm not sure. That's very interesting.
I mean, if you look at your cut or the plots of the vectors that you learned, I noticed they were sparser than the standard eigenvectors, right? On your cut, you have mostly blue. If blue represented 0, then we'd have anecdotal evidence already.
Oh, I see. I see. Yeah, that's a good point for the one-dimensional eigenspaces. That is a very good point. I should check.
Can you explain it again? Like, why does this now tell me that the eigenvectors are sparse?
I'm not sure of the color scale here, but does blue mean 0?
Honestly, I don't even know.
Okay.
But
at least we see that the eigenvector has equal value across most of the cut. So in some sense.
What do you mean? Like, if we look at eigenvector with higher frequencies, then yeah, like eigenvector 1, 0, 2, 3, then it's not very similar across the cat, and like it's basically only here that's a lot of stuff, and here that a lot of stuff is very similar, right?
Right, and to me it seems that this is the learned output of the BasisNet. So it appears to be the case that these are sparser signals that are learned there, but I'm not sure.
But I mean, we also have these other cats here.
Yeah, but this is the input to BasisNet, right? It takes the eigenvectors as input and then outputs this invariant representation of this.
Yeah. Okay. Maybe. Yeah, good. We have very little. Yeah. Okay. Convinced.
Yeah, I'll take a look at that. That's very interesting.
Cool.
Also, I have a theory. We were talking a lot about why adding the eigenvalues to eigenvectors doesn't improve performance. I wanted to add my own theory to that discussion. The eigenvectors implicitly do contain the frequency information, because the eigenvector corresponding to the small eigenvalue varies very slowly across the graph. So this might be why explicitly adding in the frequency in terms of the eigenvalue itself is redundant. But you would have to test it, I guess, to be sure. But
I don't think that's the case, because as we discussed earlier, we don't have access to the graph during the SignNet part. So during the SignNet part, basically, if you take a high frequency eigenvector or a low frequency eigenvector and you randomly permute the nodes, then they would both look like high frequencies, right? And only when your permutation is really well organized that you can see which one is low frequency and which one is high frequency.
I mean, but if you take phi as a graph neural network, yeah, I guess you could see that, yeah, the frequency.
Well, I think it's even enough if the inference model is a graph neural network, because this inference model then is likely to perform message passing of vectors, at which stage it might become clear that some of these vectors vary slowly than others.
Yeah, I agree with that. Yeah, I agree with that. Especially if like your SignNet is just like, it acts node by node, it'll preserve like some frequency, like MLP, yeah.
But yeah, I love your work. Very nice. Thanks.
Yeah, I can only agree with that. I haven't been hyped about the paper that much in some time. But yeah, then let me also make a comment here, because there was a lot of talk about the zinc dataset as well in the chat. Like I think just because you can compute something, it is not a useful task for the real world to solve, and we don't need a neural network to solve this task. But it is a good benchmark to test the expressivity or the capabilities of GNNs. Yeah, and that's the purpose of this benchmark. And it's still valuable to perform well on it, because we can hopefully maybe think that we also perform well on other tasks. Yeah, but then I also wanted to say, Josh, you said something about initial results about max cuts and doing some, yeah, using your sign net as a heuristic for some combinatorial problems.
Yeah.
Is that something that works super well? And you, yeah, can you?
Yeah, preliminary experiments show that using a sign net to compute things like max cuts and so on works really well, but that's not ready yet. That's very preliminary right now. So
okay. So we'll wait a little bit more for the next archive update.
yes, exactly.
Good, cool. Then any other questions from the audience?
I would like to say that this talk was very nice, and like the idea is so simple, but it works so well that like I think this is the kind of things that make the science progress. And I think in the field of graph neural network, where we've been using eigenvectors and eigenvalues for a long time, and kind of thinking that this sign problem and this basis problem are almost unsolvable, and we just have to deal with that. And in your paper, you actually propose like a super elegant solution that can be used in any kind of network super easily. So I really think, like, I really want to thank you for this talk. And I mean, your proposition one is so simple, like it's mind-blowing that it took so many years, like 5 years of eigenvectors in GNNs to find it, and I'm glad you finally did.
So I have to say,
thanks, Tom. Glad you liked it.
I can echo basically everything from Dom, except I have to say to me all of this basis invariant stuff is not so super simple. Yeah, but maybe you also now want to comment on Fabrizio's comments. I was thinking of an IGN as or of IGN for phi, and on.
Oh yeah. Oh yeah. Oh, sorry, I just chatted it too. But yeah, the basis net.
Yeah.
Oh, basis net uses IGN. All these you see all these like purple bars that uses IGN for phi in these experiments. Yeah.
Okay.
So Derek, Fabrizio here. First of all, great talk. Really enjoyed it, and the work is really great. So congrats. No, I mean the question was, I was wondering if IGNs, you noted maybe that IGNs work better than deep sets or transformers in particular.
Yeah, it's maybe not in particular on this task. Okay. But one important thing is this is on the training set. You see, right. Sorry, I didn't mention that. This is just a test of expressivity. So SignNet in theory is always more expressive than BasisNet because it has less invariances. I kind of don't want to say that, but like that's true. I just don't want that to be misconstrued. So yeah, we might have to look. We probably have to look at the test set to see.
Okay, then let me go with a last thank you, because it really was no, it is an awesome paper, but also was an awesome discussion. But at that point, also thanks to people like Fabrizio for the nice comments, to Emanuele for bringing up all of these additional points. Also to Professor Lee. I don't know if you're still here, but it's also thanks to you. And yeah, awesome discussion, I have to say, and thanks for making this happen. Yes, a really exciting paper and an awesome discussion. So we'll have more of these awesome discussions. Join them yourself with all of the links in the description, where you can also sign up for reminders about the next papers, and you can also join our Slack channel, for example, and suggest what paper you want to have covered next. And maybe I'll reach out to the author and we can get him on here. See you.